Hello guys, welcome to the Dynamics of Dark Energy series. This is Leonardo Cap and welcome to my channel Physics Research. In this video we are going to understand several things. First of all, we are going to understand about what is the equation of a state and what is the Newtonian way to see the cosmology. So we have two views. One view is from general relativity perspective and another view is from the Newtonian perspective. So we want to first differentiate what these two views are giving us, and then we want to understand that what is the equation of state. Followed by it, then we are going to understand that how Einstein has invoked cosmological constant and why he invoked the cosmological constant. In the previous lecture, we have already seen that the equation of a state is defined by the ratio of pressure over energy density, where omega, now for the moment, we assume that omega is constant. Therefore, we have these three sets of equations. First equation for Hubble parameter, and then we have a scale factor in terms of omega and t, and then we have rho in terms of omega and a. Now we have already told you that if omega is 1/3, it signifies the radiation dominated universe, and omega is equal to 0 means that the universe is dominated with only dust or pressureless fluid, or we can say that it has only matter type of fluid, correct? So here we have, if we have radiation, therefore the scale factor is proportional to 8 to the power minus 4, and if you have dust, then energy density is proportional to 8 to the power minus 3. Since we have three equations, like for example we have first Friedmann equation. In first Friedmann equation, it has been shown that if you have Hubble parameter, Hubble square is equal to, it depends on the energy density and some curvature term. And second Friedmann equation gives you the time derivative of this Hubble parameter, and then we have minus 4 pi g rho plus pressure and plus again this curvature term. But followed with these two equations, we have one more important equation, rho dot plus 3h rho plus p is equal to 0, and I had told you that this is coming from the Bianchi identities, in which the Einstein field equation must be, the covenant derivative of Einstein field equation must be 0. It means that the energy momentum tensor of whole the component in the universe must be 0, which says that the time derivative of energy density is plus 3 into h, which is Hubble parameter, rho plus p is equal to 0. If you want to write the second Friedmann equation, we can also express second Friedmann equation in terms of a double dot over a is equal to minus 4 pi g rho plus 3p. Now a double dot, a is a scale factor, and a dot gives you the velocity and a double dot gives you the acceleration. And we have already given that our universe has the accelerating kind of an expansion. So if our universe is expanding with acceleration, it means that a double dot must be greater than 0. If it is greater than 0, but here it has negative sign, to incorporate negative sign, it means that whatever inside the bracket rho plus 3p has to be negative. If rho plus 3p has to be negative, it means that p over rho is less than minus 1 over 3. And if it is said that minus 1 over 3, it means that equation of a state must be less than minus 1 by 3. What is the meaning of equation of omega minus 1 by 3? Here you have in the number line 0 and then minus 1. Let us say here you have minus 0.33, which is corresponds to minus 1 by 3. So anything, if you are going in the left side, it will be lesser than means minus of 0.33. It means that if you want to understand about the accelerating nature, therefore this equation of a state must be lesser than minus of 1 over 3. If you want to see the cosmology from the Newtonian point of view, what does it imply? We already know that if you have two masses, what does it imply? That the force of attraction between two masses will be given by minus gmm over r square. Now, here is our assumption. Consider the universe to be an spherically symmetric and it has a spherically distribution of the mass. Now, from the center, suppose that all the masses in this sphere is concentrated at the center, and from the center to any time of the perimeter or the surface is a of t. And this a of t is scale factor, the scale factor that we have introduced in the FRW term. Now you already know that this scale factor is time dependent. It means that if the universe was first this much, then after as the time increases, this universe is basically increasing and increasing and increasing. Hence a is kind of an always an increasing function with time. So if we are considering the universe to be homogeneous, it doesn't have any problem. Now consider that in this sphere there is a very small test mass, that is m, and with this whole mass, let us say consider that the universe has the complete mass, that is n. correct? Now I want to see that what kind of interaction, what kind of force this m is applying on, this capital M will be applying on this small m. So in order to find the motion from the second law, we can say that okay, m a double dot gives you the acceleration, because a is the position vector, dA over dt will be a velocity, and d2a over dt square gives you a double dot acceleration. Therefore I can simply express it in terms of this way. So test mass will be gone, and hence we have a double dot is equal to minus g over r square. Now we have this mass, the total mass of the universe. Now I can easily write, because we have the geometry, therefore I can express mass in terms of rho is equal to m over v. Okay, therefore mass will be rho times velocity, rho times volume, correct? So therefore mass can be written in terms of rho times volume. Volume is that 4 by 3 pi a cube. A is the radius, and then rho is some kind of a rho. Therefore we can say that this r is between a, so this is like this. Hence we can have this a square, and a will be this one. Therefore I can simply write a double dot over a is equal to minus g 4 over 3 pi times rho. Now we already know that g is a positive, pi is positive, 4 over 3 positive, and the energy density of any kind of fluid will always be positive, because rho is less than 0, rho negative doesn't a physical object. Therefore when these are positive, these whole quantity are positive, therefore this minus sign implies that a double dot becomes negative. I have already shown you that a is always positive, correct, with time. Now if the acceleration is negative, it means that this acceleration basically deaccelerating. Think about the Newton's classical mechanics. Okay, it means that if we are analyzing everything, the cosmology from the Newtonian perspective, what we are understanding that instead of the universe is accelerating expansion, it shows that it is basically deaccelerating. So whatever the content in the universe, basically it is deaccelerating. Therefore whatever the scenario Einstein present, it is completely, or the in universe, whatever the thing we are actually seeing, it is completely opposite. Therefore Newtonian perspective is wrong. Now Newtonian is wrong, but can we modify it in some sense that we can get accelerating kind of universe? Well, you can modify in terms of g. Let us say g does not hold the same value as in terms of planet, because if you are in the universe, if you are in the earth or moon or any planet, we know what is the value of g perfectly well, because whatever the experiment we are doing, we know, we have idea. But you can argue that okay, g can have different value if you are a very large scale, so maybe in the cosmic scale g can be different, or g can be have some different time signature. Maybe when universe was too young, g would have some different value, and now universe have something different. So maybe there is one sense. Another thing we are going to see that from the Einstein's perspective, rho plus 3p, but in the Newtonian perspective, what we are seeing that a double dot by a is only containing rho. Now we have already seen that rho cannot be negative, therefore that's why we are getting some problem. It means that when we generalize the Newton equation to Einstein gravity, means that when we taking care of relativistic correction, then this pressure term automatically comes. And because of this pressure, it has been signified that okay, the energy density of any object cannot be zero, cannot be negative, but yes, it can have the negative pressure. Now in 1917, Einstein has introduced cosmological constant lambda and achieve a static universe. Why he has introduced lambda? Because whenever you see in the sky, what you see, where is the star, it will remain there. So what he realized from this Einstein field equation, that if we are not invoking any kind of lambda, it means that the gravity is the attractive force. What will happen eventually is that all the matter present in the universe will collapse. Therefore, in order to have the static universe, we will have the collapsing kind of nature. So the sun that you are seeing far apart will eventually collide with Earth. That will happen. In order to prevent that, Einstein has just introduced that cosmological constant is there. Now in 1920, Hubble had discovered that no, the galaxies are expansion. So Hubble did not describe that this expansion is accelerating, but later on in 1998, people have discovered that no, whatever the thing you are actually observing, this expansion is basically accelerating, and for that the Nobel Prize has been given. From the point of view of particle physics, however, the cosmological constant experiment naturally arises as an energy density of the vacuum. Now, if you are studying the cosmology, if you are studying cosmology, then you have to invoke lambda. But if you study the particle physics, means astroparticle physics, from there is a called vacuum energy, and this vacuum energy is kind of a constant vacuum energy, and it has automatically arisen. But there are two pictures now. One is from the particle physics and another is from this cosmology. If you have the lambda in your theory, then it will give you the value of Hubble constant from the data, and whatever you are getting from the data, Hubble constant, which is different if you would study from the particle physics, and therefore it is leading you to the cosmological problem, and which is stated in the reference 45. Now there have been number of attempts to solve this problem. An incomplete list includes adjustment mechanism, and anthropic consideration, changing gravity, quantum gravity, degenerate vacua, higher dimensional gravity, supergravity, string theory, space-time form approach, vacuum fluctuation of energy density, and so on. From the perspective of cosmology, we want to understand that how Einstein had thought that, okay, I don't want to invoke any other term, but I want to invoke only constant. Now the problem is that why he chose only constant. The answer is here that now in Einstein equation there is a one fundamental thing is that Bianchi identities, where the covariant derivative of Einstein tensor is equal to 0, which leads to the energy conservation, where this energy momentum tensor, the covariant derivative of energy momentum tensor will always give you 0. Whatever the covariant derivative you will take with G mu, it always give you 0. It means that it is giving you the additional freedom in your system. How this additional freedom arises? This additional freedom gives you that this will hold good. Okay, G min is equal to 0. Therefore, again, we already know that this will already hold good. Therefore, if I am just covariant derivative of any kind of constant with this thing, it won't change anything in our G mu. So, therefore, this was the appearance of this Einstein equation, as you can see from equation 55. What is the meaning of trace? By trace the equation, we find minus r plus 4 lambda is equal to 8 pi gt. What is the meaning of? We already know that r mu nu or t mu nu, they are 4 cross 4 matrix. Now when we are talking about trace, it means that taking the only diagonal elements, these components are 0 0 1 1, similarly 2 2 and 3 3. These components, now add these components 0 0 1 1 plus 2 2 plus 3 3. These components will give you the trace. So trace of like r mu nu can be written as, let us say, r mu nu, and then since r mu nu, where mu and nu must be equal, therefore I will get r11 plus r22 plus r33 and r00. So it will give you some scalar kind of term. So r mu is basically nothing but r. So what we can achieve from here, they have achieved that they have written this equation r mu nu minus lambda G mu nu in this form, r mu nu in this kind of form. So how can we write these things in this form? I can just take one index upper, therefore this G mu nu will become Kronecker delta mu nu r plus lambda G mu nu. Now Kronecker delta has property that because it has 4 components, therefore it will become half into 4r plus lambda G mu, this will be again Kronecker delta mu nu, Kronecker delta mu nu. Therefore this will give you r plus Kronecker delta is equal to, and this is 4 delta is equal to with therefore 8 pi gt. So that is the origin of this thing. Now from here what you can do is that you can simply replace this r. If I'm going to replace this r, then everything we can write here in place of this r in the indices with the lower. So here every indices are lower and here every index is lower. Now t is very simple, correct? T we can easily evaluate for anything. If we are considering the fluid, and the fluid have this structure like minus rho, then no diagonal component, then again P and P and P. Rho is energy density, P is pressure. So if these are the metrics, therefore I can have similarly mu and mu will be minus rho plus 3p, correct? This is the trace of this thing. So to find this thing is very very trivial one. Therefore we have found out this one. Now in order to understand the impact of cosmological constant that he has introduced, the motivation of introduction, that I want to have something in my fluid equation which prevents from collapsing. It means that the universe must be static. Okay, so how to do that? So what Einstein did that, now G mu tells you that how universe is curved. So what I want to do that, I want to take general relativity in the Newtonian limit. Okay, in the Newtonian limit, what we are going to get? In the Newtonian limit, we are talking about planet and solar system. So everything here can be terms that, okay, whatever we are seeing, they are in the flat curvature, because F is equal to ma, and everything is from the Eulerian space, and Eulerian space is treated as that the space is flat. So G mu can be written in terms of Minkowski metric. Minkowski metric has signature -1 1 1 1. Therefore it is flat and have some kind of a little perturbation. This little perturbation says that, okay, this is, let us say, a background metric which is flat, and there is some kind of a curviness in here, and this curviness is very small, that sometimes the higher order terms can be easily neglected. So we will only consider up to the term of first order. Now our calculation becomes too much easy. In Newton equation we have following things: F is equal to gmm over r squared. Now if you want to say that if any planet have this kind of test mass, therefore you have gravitational field of this object, mm will be 0. This gravitational field is equivalent to gm over r squared. Now this gravity can be thought of like electric field. Gravitational field or gravitational strength is like kq over r squared. Now we have already seen that in electric field we can define as the gradient of some potential. Potential is a scalar quantity, therefore I need to do del phi. Now from the Gauss law we have already seen that. If you don't know, I have the video, you can see in the by clicking on the I button that if you compare it with the Gaussian surface, then we can write in the differential form this equation: del dot E is equal to rho over epsilon naught. Now if E will replace by this one, what we can realize is that del square phi is equal to minus rho over epsilon naught. This minus rho over epsilon naught tells you that this is kind of a source term, and this is a differential equation which will determine what is the shape of phi. It also says that if there is no any source, then still we can find the potential. And this is the problem of Laplace transformation or Laplace equation. So this equation in terms of, we can say that is a Poisson equation. Now this is completely true in terms of also the gravitational field. Now in gravitational field, let us say we can have some kind of an potential which will eventually give you a rho over epsilon naught, or simply rho over epsilon. Now if you neglect the time variation of gravitational potential, now if we calculate r00, therefore it will simply be minus half delta h0. Now this delta h0 is giving the change, okay, or del squared h0. So this triangle is giving you this thing, del nebula squared, okay. So del is corresponds to nebula square, and h00 has component of phi. This is called the gravitational potential. Therefore g00 is minus 1 plus 2 phi, and we already know that the t00, the zeroth component, is giving energy density. Hence from the field equation we will get nebula square phi is equal to 4 pi 0 minus lambda. Del square phi is equal to 4 pi g minus of lambda. Now this is the some kind of a correction because of cosmological constant, but in the Newtonian limit what we observed that we have only this equation, we don't get this one. It means that if we are in the planetary modes, in planetary system, then we can have only this much, is fine. We don't require this lambda. Then what does lambda? So if you check dimensionally, it means that lambda has the dimension of length inverse. Now if it is equivalent to Newtonian, it means that lambda has to be equal to 0, but in which case I can say that lambda to be 0. So lambda has the dimension of length square, it means that it is length square. Now if I'm increasing length to be very far, it means that now then lambda can be very small. It says that if you are working in the planetary scale, the leading term will be this much, and this lambda basically that is coming from the Einstein equation, basically working in a very large scale, means that kiloparsec, megaparsec. If you are working with planetary scale, we can easily dump this term. But if you are working with galaxy level scale, then we have to consider it. Therefore, if you are a cosmologist, then lambda is playing a role in a very large, large scale. So you cannot have any kind of significance from in the planetary motion. Therefore, that's why whatever the effect of cosmological dark energy we are seeing, we are observing from the motion of galaxies, that how they are actually going far apart. We are not detecting in the solar system. You will never detect. So if you are bind with any sun, you will always be bind with sun. Dark energy won't have that much amount of strength that it will simply give you that much push that you will go off from this closed orbit. It is not. So whatever we are observing in a cosmic scale, means a very large scale. Therefore, it is very hard to detect the dark energy in terms of if you want, in terms of laboratory what we have now. So that is the difficulty, and that's why we are not able to get everything. How is this we can find it? Now, from the Friedman equation, we can have h square is equal to the energy density, then curvature term, and then this lambda over 3. Lambda over 3 is from this equation. As you can see from here, lambda g min from equation of 55. Now the second Friedman equation will again have some modification, lambda over 3. Now what Einstein believed that our universe is static. If universe is static, it means that whatever the scale factor is constant, means that the universe has some kind of finite dimensions. The universe is not infinite, or whatever the universe is, just it is there. We could not measure this length. A is constant. It means h is equal to a dot over a. First derivative is constant, is 0. Therefore h is equal to 0. If this equation is 0, what is implying that this whole equation is 0. Now it has some kind of a correction term, therefore which is lambda over 3. Okay, and again here in 59 it is still again 0. Therefore if it is 0, therefore this lambda over 3 is equal to 4 pi g by 3 rho plus 3p. Now what does this equation tells you? In the absence of lambda, we want to determine that what could be the universe, what shape of the universe. Rho is always positive, minus 3p, p can be negative, p always be negative. Okay, p can be negative because rho has to be positive. Therefore this quantity becomes positive, therefore k becomes positive, a is positive. Therefore we can have only one thing, that if k is positive, let us say k is equal to 1, we are having that the universe is a spherical type. So when Einstein first constructed a static universe, he considered that the above solution is not physical, so added a cosmological term. From here he have introduced the cosmological term, like he have introduced that k over a square is some kind of a lambda, and lambda is positive. Therefore if the universe has to be static or closed, k is equal to positive and lambda is positive, therefore the radius becomes 1 over square root of lambda. Hence from here the density rho is determined by lambda. So whatever is the rho is, so we can find the lambda, and from the lambda we can easily find the rho. From there he introduced the lambda, but later on people have found out that this lambda that Einstein has introduced, he was wrong. The lambda has a property in such a way that universe is basically accelerating expansion, and the geometry of the universe in such a way that k is equal to 0. Therefore there is something bigger is going on. So we will understand later on that what is this bigger going on. So I hope I have explained in a better way, and if you want more videos on the dynamics of dark energy, so please subscribe and please ask so many questions, and please ask questions by write down a comment, give me a feedback how am I making and how can I improve my videos. And if you are really enthusiastic about some idea you have to tackle down dark energy, I am all. See you later.